Hello, welcome to Chapter 8, Homework Questions 60 through 66. This is Day 2 of 8.1.5. Question 60, solve for x in each diagram below. So on Part A, you see that all of the angles are x, so therefore we know that when you add three angles of a triangle up, the sum of those are equal to 180 degrees by the triangle angle sum theorem. So we have 3x is equal to 180 degrees divided by 3. And x is equal to 60 degrees. Now, I showed the math. I didn't have to because knowing that the three angles were the same, we know that it's equal angular, so therefore we know it's a 60, 60, 60 triangle. But there's the algebra behind it. B, we have a quadrilateral. We know that the sum of the angles of a quadrilateral should add up to 360. So we can do kind of the same thing we just did on the last one, but since it's a quadrilateral, we're going to change the 180 to 360, and remember the reason we know that is because you can break these up into triangles. So two triangles, 180 plus 180 is 360. Add those up and then subtract from 360. So you get x is equal to 82 degrees. Now on the next one, how many angles do we have? 1, 2, 3, 4, 5, 6 angles. So we could figure out, we can use the formula, but also don't ever forget that, if you're struggling with, remember what that formula is, remember, we can just break these up into triangles and then ask ourselves how many triangles are there. 1, 2, 3, 4 triangles. So you know that each triangle is 180, so you can take 180 and times it by 4 to get 720. So don't feel like those, if you forget, just go back to how we found them in the first place. So we know that they're going to add up to 720 degrees. So we'll take each of these and add them up. I'm not going to write them all out. I'm just going to combine my like terms as I go. So 10x, 8x, 12x, 7x, 9x, and 6x. So if we add all of those up, let's see, 20, 30, be 45, and then the 7 would be 52. Hopefully I got that right. So 52x. And then you can combine your constants, negative 16, negative 8, so that's negative 24, and then the rest we're adding positive numbers here. So I figure where was that? So negative 16, negative 8, negative 24, that's negative 22. So I think we get negative 8 there, and then that is equal to, what do we say, 720 degrees. So we can add the 8. To get 728 degrees, and then if you take 728 and divide that by 52, you will get an x value of 14. Now, the x is 14. If you wanted to find, it doesn't ask for this, but if you wanted to find each individual angle, then you're going to have to plug x back in to each of those expressions to find the angles. Part D, we see that we have two parallel lines, so that kind of stuck out right away when I looked at the figure. We also have a pentagon down here. We have three sides that are given, but we're missing, this angle right here. But we do know the one down there that's not labeled. It is because it's a right angle. So we have a total of 4 of the 5. And then it's wanting us to find x. Well, let's see where x is located in this kind of figure over here. Remember, x, we have two parallel lines. So we, know that vertical angles are congruent, so that's good. And then we also know that corresponding angles are congruent. So we could do a couple different things. This is congruent to this, and then corresponding, which would be this one right here, is also congruent. So that's x. You could have also done alternate interior angles are congruent, and then vertical angles. So either way, this part of the pentagon is x. So you are going to have 5 sides, so you can take 180 and times that by 3, which is 540. Or once again, split it up. So we get 540 degrees is equal to x plus, and then I'm just going to go ahead and add all 3 of these angles up. So that would be 423 degrees. You can subtract 423 from 540, and that will be 117 degrees. So if you add up all 5 of those, now you should get 540. Question 61. What is another more descriptive name for each polygon described below? So for part A, we have a regular polygon with an exterior angle measure of 120 degrees. Well, exterior angle measures add up to 360. So if we take 360 degrees and divide by the exterior angle measure, then that will give us the number of sides. So we know it's 3 sides, and it is a regular polygon, so not is it just a triangle, but it'll be specifically, because we want to make sure that we are descriptive, it will be an equilateral triangle. All right, part B. A quadrilateral with 4 equal angles. So a quadrilateral with 4 equal angles. Well, to have the equal angles, we're looking at a rectangle. Does it have to be a square? Well, it's not saying anything about the side lengths on this one. So to have 4 equal angles, once again, if we're thinking about kind of making sure we understand this, that if they have to be equal, then we could divide by 4 and we can see that the angles have to be 90 degrees. But that doesn't mean it has to be a square, but it does have to be a rectangle. Could be a square, but it definitely has to be a rectangle. C, a polygon with an interior angle sum of 1,260 degrees. So remember the angle sum, when we add those up, there was 2 different ways we kind of discovered this, is that we can take 180 and multiply it by the number of sides minus 2, or it could have been 180 in and then subtracting the 360 degrees. So it's the same thing, it's just one's distributed through. So I'm going to go ahead and divide by 180 degrees here. And that is 7 is equal to n minus 2. Could have distributed first, but either way is fine. Add 2, and n is equal to 9. So a polygon with interior angle sum of 1,260. So if it's 9 sides, then we're looking at a nonagon. All right, and then part D, a quadrilateral with diagonals that are perpendicular bisectors of each other. So if you kind of go through the levels of a quadrilateral, a parallelogram, do they have perpendicular bisectors? No. Then you can kind of go to a rectangle. Or do they have perpendicular bisectors? No. And then you got a rhombus and then a square. So a rhombus, if you go back and look at a rhombus, that's when they first are introduced in terms of those perpendicular bisectors. So a rhombus has perpendicular bisectors for sure, and then once again, it could be a square, but it doesn't have to be a square. It just has to make sure it's a rhombus, because a square is a rhombus. Question 62, if triangle ABC is equilateral, and if A is 0, 0, and B is 12, 0, then what do you know about the coordinates of vertex C? Prove your answer is true. All right, let's start with kind of a little visual here. We got the point 0, 0 for A, and then the point 12, 0, we're just going to kind of throw over here, just like I said, to get a visual. Now, we know it's equilateral, so we know the side lengths have to be the same. So maybe the first thing you might recognize is that length is 12, and that's a good start. So we know the rest of the lengths have to be 12, so we know it's going to do, something like this. Because it's equilateral, this is going to bisect these two, so that'll be half, which means 6 and 6. So this point will have to be 6 comma something. We know it's in the middle of those two, so that's good. What else do we know? Well, we know that these lengths over here also have to be 12. So by creating the perpendicular bisector, we know that we can find the distance, which is this right here. We're looking for this height because that'll be our y value, because we have a right triangle. So you might also recognize that this will be a 30, 60, 90. So you could use your shortcuts, and I'm going to go ahead and do that. So if the hypotenuse is 12, my short leg, which is down here, is 6, and that's true. And then my long leg, which would be the one across from 60 degrees, is the square root of 3 times the short leg. So that would be 6 square roots of 3. So the exact ordered pair would be 6 comma 6 square roots of 3. If you didn't use your special right triangles with the 30, 60, 90, then you would have got the approximation for whatever 6 square root of 3 is. And then the other thing is, if you didn't think of it this way as well, we didn't have to go up. We could have created our equilateral triangle this way. So how would that change? Not necessarily the best drawn here, but this could have also been C. It still would have been at 6, but we could have went in the opposite direction and had the ordered pair as negative 6 square root of 3. So the distance is still 6 square root of 3, but in terms of the coordinates of vertex C, it could have been either one of these. So once again, it could have been 6, 6 square root of 3 or 6, negative 6 square root of 3. Question 63. In the figure at the right, line segment AB is congruent to line segment DC. Angle ABC is congruent to angle DCB. Then the question is line segment AD congruent to DC? Prove your answer. And obviously that's not correct because that's what's given to us. So I'm going to change this. I believe we're trying to prove that line segment AC is congruent to line segment DB. So that's what I'm going to prove. So what is it that we know? Well, if you're looking at the two triangles that are interlaid together, you have triangle ABC, and then you have triangle DCB. So there you go. So if you can see those two triangles there, AB and DC are congruent, so that's a side. Then you have the angle that appears to be right, but it doesn't specify, it doesn't matter. ABC is congruent to DCB, that angle. And then what we also need to look at is the side length on the bottom here. This side length is congruent to itself by the reflexive property. And so then we know the triangles are congruent, and then we can say that their corresponding parts are because the triangles are. So let's kind of work our way through that proof. And I'm going to do a 2-column proof on this one. So I created my given statement, there's 2 of them there, and then we went and said that side length BC is congruent to side length CB, and we know that by the reflexive property. And now we have the 3 sides of the triangle. We have side, angle, side, so we know that triangle will go ABC is congruent to triangle DCB. And we know that because of side, angle, side congruency. And then since we know that the triangles are congruent, then we can say any of their corresponding parts are also congruent. So what we're trying to prove is that side length AC is congruent to side length DB. And so we know that because when we have congruent triangles, we know that their parts are also congruent. Alright, and then for part B it asks, do the measures of angle ABC, so once again that's this one, and DCB, that one's this over here, make any difference in your solution to part A. So do the measures matter? Like I said, it looks like a right triangle, doesn't say it is. Might even heard me say it doesn't even matter. So in this case, no, it doesn't matter what the angles are, as long as that the triangles are still congruent by side, angle, side congruency. So it doesn't matter what those measures are. The rest of the triangle that will always be congruent based on whatever that angle is, as long as it's congruent with the other one. Question 64. On graph paper, graph the parabola y equals 2x squared minus x minus 15. And then we're going to answer some questions. So my suggestion is you can either you can use Desmos to plug that into Desmos so you can get the graph, or use your graphing calculator. Alright, I went ahead and used the graphing calculator on my side to graph it. Now the vertex on my graphing calculator, it didn't come out exact. So I'm not saying that the lowest point is at negative 15. That was just the lowest on the calculator. So it goes a little bit lower at some point there as well. So in part A, what are the roots of the x-intercepts of the parabola? So one of them came out to be 3, 0, and you could see that on the graphing calculator. The other one appears to be crossing between negative 2 and negative 3, but how do we know for sure? Well, we can actually go ahead and solve the equation for 0. So you plug 0 in for y, and you can solve it this way. This is one way to do it. The other way is you potentially could use your graphing calculator to calculate that as well, or maybe make some guesses as to what you think it is. Does it fall exactly in between negative 2 and negative 3? I'm just going to go ahead and solve and see what happens here. This one can be factored, or you could potentially use the quadratic formula. I'm just going to go ahead and go straight to the factors here. So let's see, we have, this would be minus 3, this would be plus 5. And you can double check that, and that would be your middle term of negative x. And then I can set my factors equal to 0. And so what you'll notice is that x is equal to negative 5/2. There's the 3, which we expected. So x does fall right in between negative 2 and negative 3. And that would be the second point. So negative 2.5, comma 0. And it does say to write your points in ordered pair form. So I did that as well. So let's see what B asks. How would the graph of y equals the opposite of the entire thing, 2x squared minus x minus 15, be the same or different? And can you tell without graphing? So if you're not sure, get an idea, what do you think is going to happen, and then you can go ahead and plug it in the calculator and see what actually does happen, or plug it into Desmos. And so hopefully you've made a conjecture about what you think would happen, and what's going to happen is because y is equal to the opposite of all of that, you're just changing that value to the opposite of y. And so what it will do is it will reflect across the x-axis. So instead of your graph kind of opening up like that, it'll open down. Not the best, but that's the idea. Question 65. To decide if his class would take a quiz today, Mr. Chu will flip a coin 3 times. If all 3 results are heads or all 3 results are tails, he will give the quiz. Otherwise, his students will not be tested. What is the probability that his class will take the quiz? Alright, so if they're all 3 heads or all 3 tails, he will then give the quiz. So maybe let's just create a tree diagram. Flips the coin, tails, or heads. It's not a loss either way at this point. Then he flips it a second time, and you could either get tails or heads. So right now you have tails, but tails, heads, that wouldn't work at that point. And so then same thing happens on the one below. You could either get a tails and then a heads. Then on the next one, the third flip, the tails could be a tails again, or it could be a heads. This one down here technically doesn't matter, but it could be tails and heads again. And then this one as well does not matter because we've already flipped something different. And then the one on the bottom, you're going to get one that works and one that doesn't. So I'm going to highlight the 3 that we see where we get tails across, so all 3, and then down here we get heads across all 3. So how many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 total outcomes, and only this would be 1 out of 8, and this would be 1 out of 8, and then the rest of them would be your 6 out of 8 total. So what is the probability that the class will take the quiz? And it is a multiple choice question. So we have 1/8 plus another 1/8, which would be 2/8 or 1/4. So the answer would be B. There's 1/4 of a chance that the students will have to take the quiz. Question 66, another multiple choice question. Approximate the length of line segment AB. So we have an angle measure, we have a right triangle, and we have a side length. Set up perfect for some trig ratios here. We have the opposite side, and we're looking for side AB, and that would be the adjacent to the 54. So that means we can use our tangent ratio. Tangent of 54 degrees is equal to opposite over adjacent. Let me call this something besides AB. I'll just call it X. And then we can multiply, let's call it Y. And we can multiply both sides by Y. That doesn't solve for Y just yet. It just gets the y out of the denominator, and then you're going to have to divide by tangent of 54 degrees to both sides. So y would be approximately, make sure when you plug in 27 divided by 54 degrees that your calculator's in degrees. 19.62 approximately would be the length for AB. And is that one of our choices? Yes, it is. Choice D.